The Sky This Month with your host, Dave McDonald.
Welcome to The Sky This Month for April 2022. I'm your host, Dave McDonald, and April is a great month for planets. Particularly those of you who are early risers, there's a great show of planets. At the beginning of the month, April 5th, we have a very cool conjunction of Mars and Saturn happening in the morning, April 5th. And bookends at the end of the month, April 30th, an amazing conjunction of Venus and Jupiter in the morning sky. And they're not going to be that close again until something like 2039. So lots of things we'll be talking about towards the end of the show. We'll do a little sky talk and give you a little more detail about that. And we have a meteor shower. The Lyrid meteor shower is happening April 22nd this month, and there's so much more. In a moment, I'm going to be introducing to you our special guest, Dr. Rick Feinberg, and we're going to be talking about the latest and the greatest concerning the James Webb Space Telescope. But first, notice that the Astronomy Bowl 2022, the New Hampshire State Astronomy Bowl, we're inviting all New Hampshire high school students to come and compete and to test your knowledge. Grand prizes, $300 in cash. Who doesn't want to win $300 in cash? An 8-inch Orion telescope, which is like a serious instrument worth $700+. A week at drone camp at Laconia Airport, and that's just an amazing thing. Plus a ride in the Eclipse mobile by the New Hampshire Total Solar Eclipse Task Force. Amazing prizes. So you want to get in touch with me, Dave McDonald. There you see my email address on the screen, astromannh@gmail.com. And you can email me. I'll get you the application fee. You need to apply, or I should say register, by April 14th. So you want to get moving on getting your registration in so we can be prepared for the competition, which will be May 14th. So keep that in mind. Well, it gives me great pleasure at this time to introduce to you once again Dr. Rick Feinberg, who is the press officer, retired, of the American Astronomical Society, retired press officer, and before that was the editor-in-chief of Sky and Telescope magazine, one of the world's premier prestigious astronomy magazines, Sky and Telescope. So today the focus is going to be, get it, the focus will be on the James Webb Space Telescope. Rick, so much.
Always good to be here, Dave. Thanks for inviting me back.
With the show, absolutely.
Great.
And we spoke, I think it was back in October, about the things that were going to be unfolding, literally. Right. With the James Webb Space Telescope. And now a lot has happened. And where are we at? Tell us a little bit about Hubble. And I see you got a couple of nice models here.
Yeah,
with Hubble and James Webb Space Telescope.
I brought these two really neat little 3D printed models. They're at the same scale. We have the Hubble Space Telescope here and the James Webb Space Telescope here. And it's pretty obvious that they look really different. They're very different types of telescopes in so many ways. Hubble has, a traditional closed tube. You can see that it's got a little door to cover the front. The Webb Space Telescope isn't in a tube at all. The most significant difference is that the main mirror of the Webb telescope is 6.5 meters. That's about 21 feet. Whereas the main mirror of the Hubble Space Telescope is 2.4 meters, or about 8 feet. It's kind of hard. The scale model helps see the difference, but my first slide puts it really into perspective because you can see you've got a person there for scale. And the Hubble primary mirror is a single round mirror, which is taller than a person.
You said about 8 feet-ish?
About 8 feet, right. And then the Webb mirror is very different. It's segmented. It's got 18 hexagonal segments that together form a much larger single mirror. You'll also notice that the normal mirror it's colored like a normal mirror, right? It's colored, it's coated with aluminum, so it's silver colored. But the Webb mirror is gold. And it's not just gold colored, it's literally coated with gold.
So it's very expensive.
Yes, very thin layer.
Yeah.
I don't imagine if you took all that gold, it's probably about as much as in a ring.
Okay.
Maybe a slightly bigger piece of jewelry, maybe a bracelet, but it's spread out over, something very, very large. But the reason that Webb is gold colored is because not only is it a different shape and size and appearance of telescope, but it's got a completely different design. It's meant to observe celestial infrared radiation as opposed to visible radiation.
And the Hubble has a lot to do with visible because we have seen so many wonderful, wonderful images.
Right.
What's the advantage of going infrared?
Well, Hubble can see all the same colors of light that we see, plus a little bit into the infrared and a little bit into the ultraviolet. Webb is virtually entirely observing in the infrared. Infrared radiation is slightly longer wavelengths, less energy than visible wavelengths. And the reason astronomers are interested in infrared radiation is actually three reasons. One is that the expansion of the universe, you know that the universe is expanding, and as we've known for the past 20 years that the rate of expansion is accelerating. The expansion of the universe literally stretches the wavelength of the light that's coming to us from distant objects. And for the objects that Webb wants to see, which are the most distant in the universe, those wavelengths are shifted out of the visible entirely and into the infrared. So that's one reason. Another reason is that infrared radiation, being longer wavelengths, has an easier time getting through dust clouds. And so with an infrared telescope, you can actually peer inside clouds that just look obscured, just dark, to a visible telescope.
Right.
And you can see things going on inside, like the birth of stars. And then the other reason is that there are a host of molecules out in space. Some are even organic molecules. It doesn't mean they're alive, but they're the same kinds of molecules that occur in living creatures.
Carbon-based?
Yeah, carbon-based, carbon, hydrogen, oxygen, nitrogen, and so on. And those molecules have very distinct emissions and absorptions of radiation at infrared wavelengths. And so if you want to study things like water vapor in planetary atmospheres, carbon dioxide in planetary atmospheres, the infrared's a really great place to be looking. So for those three reasons, Webb is an infrared telescope.
Nice.
If I can show you a few more slides, another very significant difference with Webb is that it's not in a low Earth orbit like Hubble. Hubble is orbiting at about the same height as the space station. It's just a few hundred miles up. It takes about 90 minutes to go around. Webb is 1 million miles out beyond the moon, and it is out there at a place called L2, which is short for Lagrange point 2. It's a spot that's opposite the Earth from the Sun, and the orbital forces and the gravitational forces balance in such a way that a spacecraft can basically just park there and stay in the same position relative to Earth and the Sun all the time. And the reason that's important is because Webb has this ginormous sunshade. Actually, you can go to the next slide. This enormous sunshade here that's a diamond-shaped thing. It's about the size of a tennis court. And Webb has to keep that sunshade between itself, between its telescope, and the Earth and the Sun and the Moon behind it, because those are very intense sources of infrared radiation. And if you want to see faint cosmic infrared radiation,
It has to be very cold.
the telescope has to be cold so it's not overwhelmed by its own heat.
It's very cool. And these look like actual pictures of
Yeah,
the
these
real
are-
thing.
These are the real thing. These are during the construction of the telescope. Last fall, when we were talking last, this was being packed up. You'll see that on the right, the whole telescope is folded up. On the left photograph, the mirror is folded. The outer wings of the mirror are folded back. Now, the reason for this is that, as you can see, Webb is ginormous. It's so big that it can't fit in its deployed configuration inside even the world's largest rocket. So it had to be folded up. If you look at the next slide, you'll see it at the launch center. It's folded up on the left, and then it gets tucked inside the rocket's payload fairing or nose cone.
Looks like a lot of science origami.
It is. In fact, people have called it the Origami Telescope.
Yes.
Not so much because of the way it was folded, but because of the way it unfolded once it got into orbit. So it was launched on Christmas, which was great because it was like a Christmas gift to the world's astronomers
Yes.
and sky-gazing enthusiasts.
7:20 a.m., I remember.
Yeah, it was
Our
very
time.
early here, right. I was actually overseas, so for me it was a little bit later, a little
time.
more convenient to watch. Very exciting. And so over the next couple of weeks, it drifted off toward the Lagrangian point, L2, and then it began to unfold. And it unfolded with the sunshade coming out, and then the mirror unfolding, and the little secondary mirror coming out in front. Took about 2 weeks, and it was hundreds of mechanisms that had to operate. And if any one of them had not operated and they hadn't been able to get it to go, it would have killed the mission.
Yeah, 'cause you can't send a repair crew
No,
up.
it's too far away. It's 1,000,000 miles out. You know, we don't have a space shuttle anyway anymore.
No.
We don't have any spacecraft capable of getting out there to fix anything. So it was really, I would call it a miracle, except that, you know, that's what $10 billion and 20
Yeah.
years of development will buy
Exactly. It's $10 billion.
you. Yeah, for $10 billion, it's going to
Everything
work.
needs to work.
You know, that's right. Plus, of course, they had the lessons from Hubble.
Yeah.
So they tested this thing up, down,
Oh,
and
I
sideways.
know, right? And
Right.
years, in a sense, behind schedule. Just
Yeah, it took a long
fixing
time.
every little thing.
Well,
that-
they had so much technology to develop.
Yeah.
Almost everything in Webb's being done for the first time.
which is awesome.
So they get out there by the end of January,
Yeah.
and then it's time to start putting this telescope together. So the very first image they took, you can see here, there's 18 little stars.
And are those 18 different stars?
No, those are 18 images of the same star. And the whole idea here is that the telescope, you know, it goes through all this vibration and shaking in launch. Even if the mirrors had been perfectly aligned with respect to each other, by the time it got to orbit, it would be out of alignment.
Sure.
So the back of every mirror has motors on it, little pistons. And what they now had to do is they had to take every one of those 18 segments, they had to tip it, they had to tilt it, and they had to move it up and down, back and forth, so that all of the mirrors lined up perfectly with the right curvature to create one big mirror.
And I believe I read in my studying of this that the tiniest amount of movement was like a 10,000th of the width of a human hair.
Yeah, it's shorter. They can move it a distance shorter than a wavelength of light.
That's crazy.
It's amazing. And again, that's what $10 billion
That's
and 20 years
exactly
of
right.
development will do for you. So what they did now is they did that tipping and tilting to figure out which of those 18 images came from which mirror.
Yeah.
And then they got them oriented in this beautiful pattern. But you'll see the images aren't that sharp yet. So then they made some little adjustments to the mirrors because they can not only move them with respect to each other, but they can actually adjust the curvature of each one.
Each one, yeah.
And then they drove them all together to get the image of the star all in one spot. And then they worked on focus. And the next image really blew people's minds when it was released earlier in March. It shows
Just a couple of weeks ago from our time here.
that's right. And it shows that the optics are essentially perfect. This image is a bit longer exposure than those earlier ones, and you can see distant galaxies in the background here.
And that's neat to point out. Those aren't like background stars.
No,
those
those
are
are-
actually galaxies.
Those are distant galaxies.
And this is not even the science that the telescope
No, this is just a
designed
test
to
shot.
do. It's just
This is
a
just a
test
quick
shot.
test shot.
Yep.
That's right. So you can imagine what's going to happen when they're, when they're taking exposures of tens of hours or hundreds of hours, which they will
crazy.
do. So this was a selfie that the telescope took before all of that optical alignment, and then after they got it all tuned up, you see that beautiful image that shows that's the actual Webb mirror, all 18 segments in perfect alignment, and what you see is the shadow of the secondary mirror holder, which is this tripod. So scientists are just overjoyed because there is no Hubble trouble with Webb,
Which is nice.
and there's every reason to expect that it's going to just produce phenomenal science. So there are 4 science instruments, 5 if you count the fine guidance sensor, or the so-called FGS. There's a mix of different kinds of cameras and spectrographs and coronagraphs. And cameras obviously take pictures. Spectrographs take the light from the target object, whether it's a star or a galaxy or a nebula, and they spread it out like like a prism separates the colors of sunlight into different colors. Or I should say it separates the white light, which is all the colors together, into the components from red to violet.
And that way we can find out what elements are present. It's kind of like fingerprinting, forensics.
That's right. I was mentioning the infrared emissions and absorptions before from molecules. Every chemical element, every chemical compound emits and absorbs light at very specific wavelengths. And when you spread the light out and look at the wavelengths individually, you can therefore identify the chemical composition of what you're looking at. You can also tell by how those absorptions or emissions are shifted in position, how fast the object is moving toward you or away from you. The thickness of the emissions can tell you how much pressure or how much density is there. It's amazing. You can really diagnose. It's almost like a medical diagnosis. You can diagnose, what it's made of, how it's moving, how it's structured.
And it's amazing all this information we can get because you think about it, astronomy is like the only science where you can't bring what you're studying into the laboratory.
That's right. That's right. But we've learned how to make light serve as a proxy for everything else that we need to know about something.
That's nice.
And then it also has something called coronagraphs. A couple of the instruments can actually block the light of a star in an attempt to image the planet that's orbiting near it. We've got very few pictures of actual planets around other stars so far, only the very nearest stars to us. Webb is going to increase the inventory of planets around other stars for which we get images. But it's also going to be able to study the atmospheres of those planets with its spectrographs.
Very cool.
So this is an interesting picture. It shows the very center of the primary mirror, and there's this box that has a very oddly shaped hole cut in it. So the light comes into the telescope, it bounces off the primary mirror, goes up to the front of the telescope to the secondary mirror, and then bounces back through that weird shaped hole. And if you look at the next slide, you'll see that the shape of that hole corresponds to the layout of the instrument apertures inside the back of the spacecraft. So the four main instruments are the near-infrared camera, that's NIRCam, that's the instrument that took the pictures that we've seen so far.
Yes.
And then the near-infrared spectrograph, the near-infrared imaging slitless spectrograph, NIRIS, and then MIRI, which is the mid-infrared instrument. Not a particularly exotic name, but I suppose neither is near-infrared camera. So we got these four instruments plus the FGS, which are the fine guidance sensors, which enable the telescope to point at something and then stay on target and not drift off. And all these instruments are now being prepared to be tested in all their different observing modes.
With these instruments, what is the basic or one or more of the basic science objectives of the Space Telescope?
Well, as I said, Webb is interested in, we'll be looking exclusively at infrared radiation. So there are actually four science themes. Why don't you show me the next slide? It's just kind of a cute illustration indicating that Webb is basically going to go after everything in the universe, everything from the solar system out to the most distant galaxies, which are the ones that we see earliest in the universe's history. So in the solar system, we're going to be looking at planets, asteroids, comets, moons of planets, only the planets that are out beyond Earth, of course, because Webb has to keep the sun,
we don't be
and
looking
Mercury and
towards the
Venus, behind it, to try to get a better handle, mainly through infrared spectroscopy, of the components of the atmospheres of the outer planets and whether they might be able to support life. Also, some of the you know how there's geysers from some of the moons of the outer planets? Webb might be able to do some remote sensing of the molecules in those
Enceladus.
moons. Enceladus around Saturn.
Europa.
Europa. Europa has them too.
Does it have geysers?
I don't know if it has geysers, but it does have some venting. I believe, through the cracks in the surface. So basically in the solar system, one of Webb's main objectives is to try to figure out where are the very best places to look for evidence of life in the solar system. And then it's going to be looking at planets around other stars too. There's a very neat trick that astronomers figured out only within the last 15 years or so, which is that when a planet that has an atmosphere around it transits in front of a star as seen from Earth. Now we can't see the planet. It's too small. But we can see how the star's light changes when the planet crosses in front of it. And as it's entering and exiting the face of the planet, starlight is shining through its atmosphere. And Webb is uniquely well designed to study those changes in the starlight as planets enter and exit a transit, and therefore figure out what these planetary atmospheres are made of. We've only been able to do it with Hubble, with about, I think, fewer than a half a dozen planets so far. Webb's going to, again, increase the inventory of planetary atmospheres and hopefully be able to help us figure out what is it that makes a planet that's a little bit more massive than Earth sometimes become a solid super-Earth, and at other times become sort of a mini Neptune, something that's got a huge atmosphere.
A small gas giant.
A small gas giant, right. A tiny gas giant. So planetary atmospheres of planets around other stars is a big target for Webb.
Neat.
So
and then you hear of looking back to as far back as we can get to the birth of our universe.
Right. Hubble did an amazing job. You've heard of the Hubble Deep Field.
Yes.
So there was the deep field, and then there was the
ultra
deep field, and then the extreme deep field. Hubble has pushed our view of the earliest galaxies back to less than 1 billion years after the Big Bang. And so we have a picture of how galaxies evolved over the past 13 billion years, but we still don't really know how they formed and got to be what they are today. We know how they've changed over recent cosmic history, but we don't really know how they formed or exactly when they formed. By looking into the infrared, where the emissions from the earliest galaxies are now shining in this invisible light, Webb is hoping to be able to see, if not the first galaxies, at least galaxies still in the process of formation. Maybe second generation, who knows, but far enough back that we're looking within maybe 500 million years after the Big Bang. So it's going to potentially double the distance back that we are seeing galaxies.
Wow.
And then it's also, sometimes it's called an Origami Telescope, but it's also sometimes called the first light machine. Because in addition to looking for light from the very earliest galaxies, it's hoping to see light from the first generation of stars that formed in the universe. I was looking into this a little bit today and trying to imagine, how can a telescope, even a big space telescope, see individual stars within a few 100 million years after the Big Bang and, nearly 14 billion light years away. And it turns out it's not going to see ordinary stars back that far, but it might see their supernova explosions.
Interesting.
And those are going to be very different kinds of supernova explosions than more recently formed stars, because the earliest stars in the universe are thought to be much more massive than stars that are forming today, or the stars that are in our own Milky Way galaxy. And bigger stars are going to go bigger
bangs.
Bigger bangs, bigger booms. And so those are the first stars we're going to see, hopefully, is supernovas from the very first generation of stars. And those could be as early as 200 to 300 million years after the Big Bang. So we're going to be...
Which in cosmic history is
most of the way back.
To the beginning,
That's right. So we're really hoping to understand the early history of the universe much better with Webb than we have been able to understand it up to this point. There's a lot of interesting theories about the early universe and about the roles of dark matter and dark energy that are going to be put to the test in the next decade, both by Webb and by the next generation of ground-based telescopes. You think Webb is big. The next generation of ground-based telescopes on mountaintops is going to be 30 meters, which is 5 times the diameter of Webb and 3 times the diameter of the biggest telescopes on mountaintops today.
So those are obviously very, very huge telescopes. How do Earth-based telescopes compare to space telescopes when you're looking in the infrared?
In the infrared, ground-based telescopes can only look a little bit into the infrared.
Okay.
So if you think of visible wavelengths are 400 to 700 nanometers, okay? So figure 500 nanometers is about a half of a micron, okay? And infrared wavelengths are usually given in microns. So Webb is going to be looking from about 1 micron to about 30 microns.
Okay.
From the ground, because of water vapor in our atmosphere, most of the infrared beyond about 10 microns is completely absorbed. You can't see it at all.
Okay.
And most of the infrared from 1 to 10 microns is severely curtailed by atmospheric absorption. And so you can do some infrared astronomy from the ground, but in order to see the longer wavelengths and to see all the wavelengths clearly, you really need to be above the atmosphere. So, but in terms of resolution, these 30-meter ground-based telescopes will actually be able to see as sharp as Hubble and Webb, but only with the help of this very advanced technology called adaptive optics, which allows a telescope to compensate for the turbulence of the Earth's atmosphere. And that's done with deformable mirrors and very high-speed computers. And we wouldn't be building 30-meter telescopes if we didn't have that technology.
Right.
Because as you know from being a backyard stargazer, no matter how big your backyard telescope, there's a limit to how much resolution you can get, and that limit is set by the atmosphere.
Right. Yeah. Well, that's really very fascinating about the James Webb Space Telescope. And when are we expected to get the first meaningful science images?
The current schedule, which seems to be pretty much in line with what they imagined before launch, is that all of the instrument modes will be tested and all of the optics will be aligned and focused and ready to go by probably the end of June.
Okay.
So NASA has already pretty much indicated that by July we should see the first images.
Nice.
And I suspect that we'll see a few test images between
right,
now and then
some teasers
to whet the appetite. Right. But the really, knock your socks off stuff, that's going to come in July.
Nice.
It seems like a long way off, but hey, it's already April.
Oh, and I know, and we were just discussing March is gone. Where did March go?
The telescope's already been in space for three months and going on 4.
Yeah.
So
That's great. Well, hey, great discussion. Thanks for bringing us up to date on what's going on and what we're looking for to come.
Yeah.
Now, this is April 2022, and in April 2024, we have a very significant event happening, and though it's 2 years away, we just want to give it, because it's not too early to start getting ready for the total solar eclipse, April 8th, 2024. So, 2 years away.
Right, but there's a very special reason for us to be talking about it here. And that is because, as you can see in the little white circle, the April 8th total solar eclipse is coming to New Hampshire.
Now, there's nothing we can do to stop it.
We can't stop it. It's going to come.
Coming.
Now, this illustration shows that there's actually 2 big eclipses coming.
Right.
There's an annular solar eclipse where the moon doesn't quite cover the sun, so it leaves a bright ring that you can't look at. You have to use those special eclipse glasses.
Right.
That's in October of 2023. And although the annular phase won't be visible from New Hampshire, the whole country is going to have a partial solar eclipse.
Yeah.
And then only 6 months later, on April 8th, 2024,
179 days.
we get the total eclipse, which is coming to New Hampshire. And it's going to go through Coos County up in the far northern part of the state.
Yeah.
And if you can, there we go. We have the next slide shows that the event will occur from about 2:15 to 4:45 in the afternoon.
Yeah.
But right in the middle at about 3:30, there's going to be 3.5 minutes of total solar eclipse when the moon completely covers the sun's bright face and its spectacular outer atmosphere, the solar corona, becomes visible. It gets as dark as deep twilight in less than a minute. Imagine if sunset took only a minute. That's what it's like for a total solar eclipse.
Well, and having been to one, and I know you have as well, in Kentucky in 2017
17.
it was, August 21st, and it's amazing. It's like the lights are dimming, but then all of a sudden it's a
Boom. It's just, yeah.
it's gone. It's crazy.
It's remarkable because in the last minute, as a total solar eclipse is about to happen, it gets 10,000 times darker.
Yes.
I mean, it's just boom,
Yes.
lights out. And then you see this spectacular thing in the sky. Now, for people who did see the 2017 eclipse, I'm sure they're very eager to see another. Usually the first thing somebody asks after a total eclipse ends is, when's the next one?
Yep.
Well, in 2017, the next one for us in the US was only 7 years away. It had been 38 years since the previous one.
Right.
And for people who didn't make an effort to get into the path of totality last time, they heard from friends and relatives who did that they missed the big show. And so now they get a second chance.
Yes.
And for us in New Hampshire, all we have to do is drive to the northern part of the state.
Yeah.
And hope
Get up-
for clear skies,
get up
which
to
in
Coas
early April,
County.
you got to cross your fingers in early April for clear
And
skies.
it's important to note that, even though you may see information, and we'll be doing shows along the way coming up to it, that there are places in New Hampshire where it will be 98, 99%. It's not the same thing as total.
No,
Even 99, you might say, I'm good enough, I got 99%. It's not the same as total.
No. 99% of a total eclipse gives you less than 1% of the experience.
Yeah.
Because again, factor of 10,000 in darkness, just in that last percent.
Yep.
And all the phenomena that people rave about with a solar eclipse, where you can see planets in the daytime,
Yes.
where you've got beautiful sunset colors all the way
Yes.
around the horizon, where birds go nuts and animals go nuts and dogs start barking and cows go back to the barn. None of that happens in a partial
crickets
eclipse.
start chirping.
Not even at 99%. It's got to be 100%.
Yep.
All or nothing.
And because, New Hampshire, Coas County, we've got, a lot of forested land up there. There's not a lot of hotels, bed and breakfast places, so make your reservations early, get campgrounds. It's not too soon to start making reservations and making your plans.
And luckily, because the eclipse occurs in the afternoon, people will have an opportunity, if they're staying in Concord or staying, somewhere else where there's a little bit more lodging, to get up to the eclipse in time for
To
it.
drive up.
Yeah.
But you want to plan that ahead too, because what do we have? Route 3.
Yeah,
So-
there's not many ways in or out. I think a lot of the parks up there are going to, they're talking about it now. They want to open up early. I know it's mud season, but that's when the eclipse happens.
You got to be ready for it.
And a lot of people are
will
going to want to be
willing
there.
to do it. Yep.
So parks will open. There's talk about maybe doing some shuttle buses up and down, and trying to keep people from leaving right away. Maybe having a fireworks show that night or a concert or something, so that people don't all jump in their cars right after the end of the eclipse and end up driving
on the
up-
road for a day.
driving up an hour or two to get there, and then spending 2 or 3 times that to get
Right.
back.
Yeah. Go early and plan to stay late.
Exactly.
Have a good time.
That's the best advice.
But hey, Rick, thanks so much for being with us on
Thank
the
you,
show
Dave.
once again.
All
And I'm sure along the way, June, July, we can touch base again and see what has happened.
Yeah. We
with,
look forward to seeing
James
those
Webb.
first images with you.
Yes, that sounds great. Thanks again.
Okay.
All right, well, let's take a look at what is going on in the night sky early morning and right after sunset. There's some great things to show you. One of the great things about this April is it's going to be the best in a long time to see the planet Mercury, elusive Mercury, in the evening shortly after sunset. So we're going to tell you a little bit more about Mercury as the month unfolds. But right now we're looking at April 5th, early on in the morning, April 5th, an hour or so before sunrise. We have a tremendous conjunction happening, and you can see like the words are like superimposed on top of each other. We've got Mars and Saturn so close, 24 minutes of arc apart. You may say, well, what does 24 minutes of arc mean? A full moon's width is 30 minutes of arc. So these two planets, Mars and Saturn, are going to be closer to each other than the width of a full moon as you look at it up in the sky. And so you don't want to miss that. That's early morning, about an hour before sunrise on April 5th. And you can see Venus. Venus is with us all month in the morning sky. We're going to visit it again. Venus is around all month, but the other planets are going to be doing a dance around Venus. But April 5th, don't miss it. Tuesday morning before sunrise, check out Mars and Saturn. Now, the day before, the day after, they're going to be close. So if it's cloudy, if it looks like it's going to be cloudy on the 5th, check it out the day before, the day after. They're still going to be close, but they're almost on top of each other on April 5th. Next, we're going to jump ahead to April 17th. We're still in the morning, April 17th. Look at this alignment of the planets. This is really pretty amazing. We've got Saturn, Mars, Venus, and Jupiter all lined up in a line like this. It's an amazing alignment of the planets. This is the morning of April 17th. Again, probably 45 minutes or so before sunrise. And jumping ahead just to talk about the date to April 25, 26, 27, 28, the moon is going to join the show. The moon is going to enter and it's going to slide down below Saturn, below Mars each day, below Venus. So I don't have a slide for that because that would be too many slides. But just so you keep in mind, this is April 17th, but April 25, 26, 27, 28 in the morning, the moon is going to join in the show, and you're going to see the moon coming down from here, down underneath the planets, and it's going to be beautiful. What a great month for the morning early risers. Well, late in the afternoon, next slide, same date, April 17th. In the original slide, there was a tree in the way, so I got rid of the tree. So, and it's important to note, Mercury and Uranus. I mentioned to you already that this is a great month to see the elusive Mercury somewhere between an hour to half an hour after the sun sets. Binoculars will be a help, but it's going to reach a point we call greatest eastern elongation when it's going to be furthest away from the sun around the 21st of April, which is awesome. But on the 17th, the bonus is Uranus and Mercury are going to be so close, they'll be in the same binocular field. And Mercury will be shining at about a -1 magnitude, which is very bright, but there's still some light in the sky. And Uranus is shining at about a 5.8, 5.9 magnitude, which is right on the edge of human eye visibility. So you're not going to see that without binoculars. But they're going to be about 2 degrees apart. And so a binocular field should get them so you can see both of them in the same binocular field. So that's a great opportunity to find Uranus. There's another star in the same field, about the same brightness as Uranus. And the one closer to Mercury is Uranus. And if you have a telescope, so much the better, because Uranus will display a small disk where stars are pinpoints of light. Planets do show a discernible disk. So you'll be able to tell the star from Uranus with a telescope. So keep that in mind. This is after sunset, and you can see we're kind of getting the last images of Orion. Orion is getting ready to set into the glare of the sun, but we still have some more time enjoying Orion as April comes to a close. Next, we have April 22nd. I mentioned to you early on in the show, we have the Lyrid Meteor Shower, and it's called the Lyrid Meteor Shower because the meteors appear to be coming from a radiant point in the sky in the constellation of Lyra. And you can see right here, you have the Lyrids, that's where the radiant point is, and this is the bright star Vega, which will be ruling the overhead in the summer. Vega is a magnitude 0 star, very bright. It's the brightest star in the area. This is 1 o'clock in the morning, April 22nd. So late night, April 21st, early morning, April 22nd, it should be a decently active meteor shower and the moon won't be a bother. So keep that in mind. Late night, April 21st, early morning, April 22nd is the best. But a couple days ahead, a couple days after, still good. The shower is still active. I'm just telling you about the peak. So again, this is looking east. As you can see, the big red E looking east. This is 1 o'clock in the morning. You can't miss Vega. And you can look all over the sky. But if you trace a meteor backwards, and it appears to be coming from near the star Vega, you know that is in fact a Lyrid meteor. If it seems to be shooting across the sky from some other direction and you don't trace it back to near Vega, it's what we call a sporadic meteor, of which they can happen anytime, any night. So notice we have the summer triangle, 1 o'clock, April 22nd in the morning. The summer triangle is out. Altair, Vega, which is in the constellation of Lyra, thus the Lyrids, and the star Deneb. Those three stars make up the summer triangle, and I can't wait to hit the beach in the summer. Next slide. We're going to the very end of the month, April 30th, and once again, notice you see these words on top of each other. It kind of looks like Jupiter us. That's because the word Jupiter and the word or the name Venus are superimposed on top of each other, because Jupiter and Venus, they're both really bright. Venus, we're talking a negative 4.1 magnitude. Jupiter is a negative 2.1 magnitude. They're both way brighter than the brightest star Sirius in the night sky, and they're going to be so close, almost on top of each other. They're not going to be this close again until the year 2038, so we're talking like 17 years for them to be this close again. So this is the early morning before sunrise of April 30th. Again, the day, a couple days, if it looks like it's going to be cloudy, a couple days before, a couple days after, they'll be close. But their closest approach is going to be the early morning of April 30th. And the neat thing about this whole month of April in the morning is you can see the planets are like moved in like different places. You've got Saturn and Mars, Jupiter and Venus throughout the whole month. If you get up early to go for a jog or go for work, every morning the planets are going to be shifted a little bit, and you can kind of imagine the fact that they are wandering, that they are in orbit around the sun, changing their position as they move around the sun, as Earth changes its position as it moves around the sun. It's just a great dance of the planets in the morning for the month of April. Hey, I hope you enjoyed the show. Don't forget to check out astromannh@gmail.com or write to me, Dave McDonald, particularly if you're interested in the New Hampshire Astronomy Bowl for all New Hampshire students, because registration is open till April 14th and the competition is going to be on May 14th at the McAuliffe Shepherd Discovery Center. I'm Dave McDonald for The Sky This Month. I hope that you enjoyed the show.